So chapter 11 is about these things called solutions. And then there's also a section at the end about these things called colloids, which I hope that we get to talk about, but some semesters I just kind of ran out of time, and so we don't really talk about them in great detail. We'll see. Solutions, though, for sure. Got a lot of stuff to talk about with solutions. So this first set of lecture slides for this chapter, so this is now our third set of PowerPoint slides, so lecture 3 in chapter 11 folder on Blackboard. And I think the first 3 sections, section 1, section 2, and section 3, are what are on this lecture slide set. This is what I'm going to try to talk about today. These first 3 sections, okay? And then we're going to say section 4 for Monday. And then we'll talk about colloids if we have time to. Okay, so let's talk about dissolving. Or this be fancy. Let's just use this fancy word, dissolution. Okay, dissolution. It just means dissolving, y'all. In fact, we're even going to use another fancy word for dissolving here in a minute. What is a solution? A solution is a homogeneous mixture. If you remember back from Gen Chem 1, when we very first learned how to classify matter, there's pure substances, elements, compounds, and then there's mixtures. And of mixtures, there can be 2 types. What are the 2 types? Homogeneous is one. What's the other type? Heterogeneous. Okay. So when we use when we use the term solution, it is a homogeneous mixture. What does it mean to be homogeneous? Same composition throughout the entire substance mixture. Okay, so to be a mixture, you have to have 2 or more components. Okay, we need to learn the word solute. Solute refers to a component of the mixture that there's less of. There's the good marker. That's the one I want. Component there's less of. Okay. Can you have multiple solutes? Yeah. But you're only going to have one solvent. Solvent is the component there is more of. Okay. You can have solutions in any mixture of phases. What do we commonly think about solutions as being? We do tend to think aqueous solutions, and that's most of what we work with, but it doesn't have to just be aqueous. Any homogeneous mixture is a solution by definition. Our air is a solution. We've talked about this. What's the main component of our air that we're breathing? Nitrogen. So nitrogen would be the solvent in this terminology. Oxygen is a component of our air, but it's in a lesser amount. So oxygen would be a solute in the solvent nitrogen, right? Any kind of metal alloy, brass, bronze, steel, you have a mixture of metals, that's a solution. There's something that there's more of, and then there's something that there's less of. Okay. Moving on. Let's think. When we try to make a solution, okay, when we're making a solution, there's actually 3 steps that are happening. Okay. And all of it has to do with IMFs. All of it has to do with IMFs. First IMF that we have to think about is between solute molecules. Okay, so let's think about that. Step one. Here, let me get out erase the board because I want to stay right here. Okay. Yes, everybody. I want to stay right here. What has to happen for a solution to form to the attractive forces between your solutes? Ooh, that's not what I meant to hit. The solute attractive forces have to be broken apart. Step one. Solute IMFs must be broken. How do you break IMFs? Can I just put a capital E for energy? We got to add energy. So what would be a delta H, an enthalpy value for this first step? A positive value or a negative value? Yeah, enthalpy, it's got to be positive. You got to be added energy to break these IMFs. What else has to happen for a solution to form? To get a homogeneous mixture of solute and solvent, not only do we have to break solute, we got to break solvent as well. We got to break the solvent IMFs. And again, how do we do that? We add some energy. Where's the energy coming from? The surroundings, right? That's where all energy comes from for a system. It comes from the surroundings. A delta H for this breaking would also be endothermic, right? Positive. And then the last step, the most important step, is here's our another fancy word, okay? Here's our fancy word, right? Instead of saying dissolved, instead of saying dissolution, here's the word that you're going to see. This step is called solvation. Solvation. What happens during solvation? New solvent, solute, IMFs form. When new IMFs form, what happens with the energy level of our system now? It's going to release energy. When those new IMFs form, energy gets released. So this step, this solvation step, a solution being made, this step should always be negative. It should be, that should say H2. Sorry, hang on. I was going step by step. H1, H2, H3. The solvation step should always be exothermic, right? From an energy point of view, will a solution actually form? Well, what we're going to do is first think about, when I say will a solution form, I mean, do the two pieces actually mix together? You guys should know that some things don't mix, right? Y'all know that? Can you give me a classic example of something that doesn't mix? Oil and water don't mix. You're like, why does that water look so freaking gross. Somebody put food coloring in it at some point. I don't know. Oil and water don't mix. I can try to force it to mix, but it is not really mixed, is it? Okay. We're going to talk about a couple of reasons why this doesn't happen. But let's just first look from an energy point of view, why it would form or why something will not form. Okay. So this first is just from the energy point of view. Okay. Oh, I'm sorry, guys. SOL'(N) is my abbreviation for the solution. Remember, the solution is the mix of both solute and solvent, right? Okay. Well, so if you guys are math people. You guys are math people. What does it mean if I put those vertical lines around this little equation I wrote? See, y'all know what that means. It's absolute value. So I'm not talking about positive, negative. I'm talking about the magnitude of adding these two things together. If this magnitude, adding step 1 and step 2, breaking, is greater than, no, I want to do it the other way first, sorry, is less than the absolute magnitude of, what is step 3? Solvation. Forming new IMFs. Okay. If this magnitude is less than this magnitude, yes, the solution will form. And it will be you're cheating, you're looking at the slides. Nah. It'll be exothermic. We're going to see an overall what? Release of heat from this system, right? Okay. If, what am I doing on time? Whatever. It is what it is. Thankfully, we can have double lecture today, guys, because we don't have a lab planned. It does indeed say work day. We're going to work our asses in lecture. Now, if the absolute magnitude of breaking the bonds is bigger than what gets released when the new IMFs form, guess what? Yes, this solution will still be created. But it's going to be endothermic. Meaning in order for it to happen, it's got to get a little help from where? The surroundings. It's got to get a little extra help from the surroundings to make this happen. But then if that breaking of bonds, okay, if that breaking of bonds is just too much bigger than anything that would be released, no solution forms. We're not putting an exact number on it. It's just in general, if the energy cost is too much, a solution won't form. To know the actual value, you have to be looking at actual real examples. Depends on the substances, 100%. Okay. Look at this. We don't need to know that. Let's talk about this. So let's talk about not an energy point of view, but a concept kind of point of view. Y'all know this rule, don't you? Y'all heard this, the golden rule of solubility? You never heard that? You know the regular golden rule, right? Okay, treat others like you wouldn't want to be treated yourself. Okay, So the golden rule of solubility in chemistry is this phrase, like dissolves like. Like dissolves like. What does that mean? Solutions form when solute and solvent have similar polarity, which we now know means they have similar IMFs, right? Solutions form when they have similar polarity, which means similar IMFs. That's it. That is why what and what don't mix. Oil and water don't mix.
Not all of that is on the slide that you put on.
You know why? Because I updated this slide last night, and I guess I didn't update it in Blackboard. I will update it for sure. So let's be sure we know why, like what is going on when we say like dissolves like. Similar, what did I say? Polarities, which means that they have similar IMFs, will form solutions. Non-similar do not form solutions. Polar and non-polar in particular is what we're saying. Do not mix. Polar and non-polar do not mix. Why is oil non-polar? I don't know that I know I talked about this in Gen Chem 1. I don't know that I talked about this with you guys earlier this week. So let's just make sure I say it now, okay? What? Sorry. It was my dentist. They want more money from me. I gotta go get a crayon. Sucks. Okay, why is oil non-polar? What is oil made of? Bunch of chemicals. You know, it's actually really only made of two elements. Really. It's carbons and hydrogens. And so I taught many of you that at the end of Gen Chem 1, that the bond between a carbon and a hydrogen is considered what polarity? Remember? Non-polar. Any compound with nothing but carbons and hydrogens, I don't care what shape it is going to be what polarity? It's non-polar. All the time, every time, no ifs, ands, or buts, and I never ever get to say that in chemistry, do I? But I'm saying it now. It's only if there's some oxygen in there, then the rules go out. Okay, then it's polar, right? Okay. Oil is made of nothing but carbons. We call those hydrocarbons. You know hydrocarbons, right? Hydrocarbons, fossil fuels, oil, gas, gasoline, hydrocarbons. They are non-polar. They do not mix with other polar compounds. All right, so what will mix with polar? Water, though, because we said water is really the main aqueous solution that we like to use, right? I mean, that's why we say aqueous. So let's think, what kind of solutes will dissolve in water? Any other polar solutes? will dissolve. What's a polar solute? And maybe give me an example of some other kind of polar compound. I got a good one. Sugar. Sugar polar? Guys, look at all those oxygens. And not only is sugar polar, so when I say sugar, actually the name of sugar is sucrose. Sugar. Sucrose, this compound right here, has 12 carbons, 22 hydrogens, and 11 oxygens already. So not only is sucrose polar, it can also do what? Hydrogen bond. Man, this really will dissolve in water, won't it? It does. Okay. Some of those other polar compounds we looked at the other day, like ethanol. Any of those alcohols, you remember those? No, because we didn't really talk about them very much. Okay. Here's another example. That's not an E, that's an E. Ethanol. Here's its formula to remind you. CH3, CH2, OH. When you look at that formula, you should be able to tell me, yes, that's polar. Why? That OH group, that O in particular, that oxygen. And it's an OH, which means ethanol can also form what kind of IMFs? Hydrogen bonds, right? Will ethanol dissolve in water? 100%. Yes, absolutely. Okay. Here's a new IMF. I told you guys earlier this week we were going to talk about ionic compounds. Here's where we're going to start talking about ionic compounds. Polar solvents, like water, can dissolve ionic compounds. Are ionic compounds polar or non-polar? This is a trick question. This is a trick. They're neither. They're not covalent at all. They're ionic. Polar and non-polar only refer to covalent compounds. Ionic compounds are not polar or non-polar. They're ionic. But polar solvents, like water, can dissolve, or what's the word that we use? Solve. So the way you would write it this way is you solvate. Dissolve, solvate. Ionic compounds. How? Well, the same energy things we talked about still have to be true, okay? You still have to do what? Break what's going on in the solute, break what's going on in the solvent, and form new solvent solute IMFs, right? Okay, so this new IMF for ionic compounds with polar solvents is called ion-dipole attraction. Look at the screen. So when you're dissolving something, right, we've got to break up what's going on in the solute. In an ionic compound, what's going on in the solute? What's going on in an ionic compound? This is a very strong positive negative ionic bond, right? This is very strong. This is an actual ionic bond, right? What's going on in the water? We know, we talked about this. What's going on in the water? What is water doing with itself? What kind of IMFs does water have going on with itself? Hydrogen bonding, dipole, whatever, you know, I mean, it's, but okay, so here it is, right? The water actually pulls the solute apart. It pulls the ions apart. How can it pull them apart? With its dipole. With its dipole. Water's dipole. Look, see? Partial positive oxygen pulls what ion out of the solid? I meant partial negative. Did I say partial positive? Sorry. Partial negative oxygen pulls the cation out of the solid. Pulls it. The partial positive hydrogen pulls the what? The anion out of the solid. Positive and negative attract, guys. Okay. Ion-dipole attraction. Okay. I'd like for you guys to, let's do this. Then let's take another little break. So I gave you guys some stuff to demo with yourself. That's the test tubes and the little trays of solid that I have set out. I want you guys to take the thermometers that you have and go ahead and just measure the temperature of the water in each one of these test tubes. So like you guys back there, I put one there behind you. Y'all can look at that one together. Y'all can look at the one behind you, boys. Y'all measure there's one behind you, John. Y'all measure the water's temperature, okay? And then you're going to dissolve a solid in it, and we're going to see if a solution forms, okay? Look behind you. There's not a thermometer there? What did I do with it? Ah, there it is. Okay. So just try to get an approximate temperature, right? What is it? Should be, I would guess probably it's going to be around 23-ish degrees C, both of them. That's about room temperature in here. Nah, that's fine. It'll be all right for this. Okay, so the first thing I want you guys to try to dissolve is this compound. And this is actually what we're doing here is we're working in class number 1 as we do this demo, okay? First thing we're going to dissolve is this compound. Can you guys tell me the name of that? Calcium chloride. Okay. According to solubility rules that you learned in Gen Chem 1, you should be able to predict that this will dissolve in water, and it is going to. I'm going to ask you guys to dissolve it and then check the temperature change, and feel it even with your hand. Okay. Which one is the calcium chloride? On your little trays, it is the ones that are the little white ball looking solid. Go ahead and find that one and go ahead and dissolve it in your water and stir it around with your thermometer, and let's see what happens to the temperature. Dump the whole thing in there and then stir it with the thermometer. What does that mean if it starts to melt as it's quote unquote melt as it's exposed to the air? What's that word we learned in lab? The
Hydro.
hygroscopic. Mhm. The calcium chloride is indeed a little hygroscopic. It is absorbing moisture from the air, so it might be kind of stuck to the little plastic tray a little bit. You might need to scrape it down with the tube. Okay, so now, yeah, all of it. Okay, stir it around. Everybody feel it on their hand. Everybody feel it, or on their wrist. Feel it. The bottom of the test tube. Feel the bottom of the test tube. What are y'all seeing happen? Okay, temperature rising. How does it feel? Can y'all feel anything when you touch it on the bottom? Feels hot, huh? Yeah. Okay. What does that mean? When we dissolve calcium chloride in water, that process, that dissolution process is what? Exothermic. It releases heat to the surroundings. That's what we're feeling. That's what we're measuring the temperature of. Okay. So what I want you to do with this calcium chloride is write what is known as the dissolution, or we might call it, I don't want to use the word yet. Never mind. We're just going to say dissolution. We're just going to say dissolution for now. Dissolution equation. How does it dissolve? What is the water doing to the calcium chloride when you put it in there? What did we just learn that the water does? It separates them, right? It literally pulls them apart. You show that in a dissolution equation. You are just simply showing the ionic compound split into its two ions. Now you got to remember your ion charges. This ion is in water, right? It's aqueous. How many chloride ions are there in this formula, in this unit cell? Two chloride ions. Yes? Yeah, that's the other word that I used before. A dissolution equation is like an ionization equation. Yes. How many total ions did we get when we dissolved a unit cell of calcium chloride? How many total ions do we end up making on that side? Good. Y'all remember that. Count how many ions get formed. Y'all remember that. Okay. Let's do another one. Let's do magnesium sulfate. Who remembers how to name this? What kind of compound is this, where I have those little dots and then the waters? An ionic hydrate compound. A hydrate. Hydrate. So how is this named? Magnesium sulfate. What is 7? What's the number? Heptahydrate. Perfect. Good, you guys. But magnesium sulfate heptahydrate is also known as Epsom salt. So that's the other tray you have. That's the kind of flakier looking stuff. So put that into your other test tube. Let's dissolve it and observe the temperature change. Okay. And I hope I gave y'all enough of this to see the effect. This one you may not be able to feel so much, but by checking the temperature, you should see what happens. Can you feel it? Can you feel it different? Oh, yeah, I can. Okay. That feels nice, actually. Yeah. Hang on, let me put it on my forehead for a second, y'all. Woo. Yeah, cool myself off a little bit. Okay. Because it got cold, didn't it? And y'all see the temperature drop? Okay. What does that mean this dissolution process is? Yeah, endothermic. Oh, I got my endothermic. Sure is. Let's write the dissolution for that. What is the water doing when we dissolve this compound? Splitting the ions apart. So this hydrate, Veronica, what do I need to do? Move this way? Is that good? And when a hydrate like this splits up, you get the cation, so magnesium 2+. You get the anion. This sulfate ion is absolutely a polyatomic ion. You got to know. Okay. And then because this is a hydrate, you also end up with just the 7 molecules of water being released as well. Okay. Oh, yes, thank you. The liquid phase for water. Yes, sorry. And this should be aqueous. Sorry. The whole compound, we put it in the water. Okay. Okay, so we said that this first one was exothermic and that this second one was endothermic. And then what does that mean about overall breaking of IMFs or forming these new IMFs? If it's exothermic, what does that mean? The forming of the new IMFs was more than the total cost of breaking the original ones, right? That's what exothermic means in this sense. And if it's endothermic, what does that mean? The total cost of breaking solute, salt, all those IMFs was more than what was released when these new ones were formed. But that doesn't mean it can't happen. It happened, right? It just needed a little extra help from the outside. Okay. Oh, you guys, okay. Let's take a break. Let's take a big break. Let's take 10 minutes. Let's take 10 minutes. And then let's come back in here. And we got to get through. We got a lot, actually. We're going to try to get to. Well, okay, we're going to go to the next section. We're going to go to section 11.2 when we come back. So let's take a break.